Hello everyone, this is Human Hard Drive, and today on Electronics 201 we're going to be talking about something that's pretty crucial when it comes to digital electronics, and that is logic operators. Now, logic is a crucial part to digital electronics because it lets you. It is the basis of all digital electronics. I mean, your computer processor is based around NAND logic or NOR logic or all this really basic AND or XOR NOT, all these basic switch statements that, when put on top of one another, make these grand things. So, today we're going to go through all of the logic operations and what they mean. So the first one is NOT, and that usually looks like this. So let me redraw that. That's a NOT. It's something with a bar over it, and logic schematic looks like this. So this triangle defines buffer. That's a buffer, means value in is value out. This dot at the end is what inverts it. So you'll see that in some of the other logic symbols we go into. Now, NOT is a single, requires a single operand, and this is, when you look at logic gates, you see truth tables. So it's a single operand, so you have A, which is one input, and then the output being not A. So, and then it steps through binary counting like that. So 0, 1. So if A is 0, not A is 1, and if A is 1, not A is 0. So it inverts it. It switches it from true to false and from false to true. That's NOT. NOT is easy. So NOT is the only single operand logic operator, but it is applied to other logic operators to create an inverse. So let's start with the next one. AND. So AND looks like this. So this is two operands, it's A and B, and the general denotation for this is A multiply B, and you'll understand that multiply in a second. So if we look at the truth table, A, B, A dot B. There we go. So if we count 0, 0, 0, 1, 1, 0, 1, 1. So A and B both are zeros, so the output is 0. A is not B, so that's 0. A is not B, 0. A is B, so that's 1. So you can see that A and B is only true when both A and B are true. Now, the AND, you can see why it's multiply. 0 times 0, it's this dot. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. So it sort of acts like a multiplier thing. Now, AND also serves to be a destroyer or a destructor of data. And I say that because only one input for the truth table creates a true output. So if I have one in the A column and 0 in the B column, that 1 goes away. Or if I have 0 in the A column and a 1 in the B column, the 1 still goes away. There's no way to keep it unless they're both 1. So it destroys data. Most of the data is 0, so it destroys it. Now that's different than the OR gate. So OR looks like this. And A plus B, and you'll understand why that is. And again, this is two operands. I should say that's two operands minimum. You can have 3 operands, but you usually concern yourself with just 2 operands. But I mean, 3 operands for AND would be C, and again, it's only true when all 3 of them are the same. So A, B, A and or B. Make your truth table, and you count 0, 0, 0, 1, 1, 0, 1, 1. Okay, so 0 or 0 is 0, 0 or 1 is true, 1 or 0 is true, and 1 or 1 is true. So you can see, again, it has this add quality. 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. It's a little complicated because there's this idea of a carry, but we're not going to concern ourselves with that. So, as opposed to AND, which is a destructor, this is a preserver of data. It preserves data because the majority of the outputs is 1. So it protects data. So if you have a 0, even though you have a 0 in the A column and a 1 in the B column, that 1 still carries through. It's preserving that data. So, another thing I should highlight, this. Oh, whoops. This is an AND component to the OR thing. So normally when you say OR, it's one or the other, not both. So it does have an AND component in here. There is a logic gate that is just this area, but we're going to talk about that next. And that component is XOR. That's exclusive OR, so it's exclusively OR. And the symbol for that is this. So it's like the OR gate, except it has that little extra curve, and the symbol for that is, I believe, a wiggly. Yes, I called it a wiggly. Helps you remember. And again, this is a 2 operand. Again, the only one that is a single operand is not. So A, B, A, wiggly, B. Draw the table. 0, 0, 0, 1, 1, 0, 1, 1. Okay. So it's like OR, except it doesn't have this AND component. So 0, 1, 1, 0. So it just takes this, and it only applies to this. It leaves the AND component out. So if we go back to the AND is a destructor, OR is a preserver. This is sort of neither. It's a different combination. It's sort of like a flipper. If something's on, it's off. So it has a certain inversion quality, but it doesn't pertain to being either a preserver or a destructor. So it has its own unique purpose that you need to find. So there's NOT, AND, or XOR. Now, NOT can be applied to each of those gates. So you can have a NOT or a NOR. You can have a NOT AND or a NAND. And then you can have a NOT XOR or a NEXOR. If we look at the symbols for those, oh, that's not. So it's that dot again. That dot means inversion. So when it's NOR, what you do is you just go back to the OR table and you flip the output. So A or B is true and everything else is false. XOR, true, false, false, true. So it just flips it. And what you can also do with what else you can do with the NOT is you can flip inputs. So you can have an AND gate with one inverted input, or you can have a AND gate with 2 inverted inputs and an inverted output if you want, or you can have an OR gate with an inverted output and an inverted input. Again, it's just that circle means not. So one more thing I want to talk about, and that's solving things. Now, these things, I gave an analogy to them being sort of mathematical operators, and they are, because they behave in certain ways. So generally, when if you're using logic operators, say in programming, you're using them to generate masks to preserve or destroy data. So if I have, say, a nibble of data, and I need to get a final output of, I need to figure out some way to get this. Now, excuse me. If I look, this 1 is going to 0. It's being destroyed. So if it's being destroyed, that's usually an AND. So that's 0, 0, 0, 1. 1 is the only way to preserve data in the OR gate. So it's destroying everything that you don't need. If I had the same nibble of data and I wanted, I don't know, if I wanted to add to it, so I want this as the output, I'd use OR because I'm adding to it. So I'd use a 1 to preserve it and a 1 to add to it, and there we go, and it stays the same. Now that's just single step. You can have multi-step where you start out with 1, 0, 0, 1, and you end up with, all the way down here, 1, 1, 0, 0. And again, it's just you taking their in-between steps. So you say, you go back to this and say you add first. So you add this, so OR, and then you say AND. So that'll add that, and then you say 1, 1, 0, 0, and that gets you that. Now these things I'm applying to it, these, if I were to, there we go. That, this, and this, and these two things here, highlighted all, there we go. These are called masks, or logic masks. And what they do is they mask various pieces of the data to get you some final output. They're masking what it was originally to give you something new. And really that's it when it comes to logic operators. So a lot of these things, if you were to just Google NOT gate or OR gate or AND gate, you'd find the truth table and the schematic and the symbol for it and its purpose. So these things are really easy, and once you get into them, they become almost second nature. You start thinking in terms of logic. So I have this and I need to get to this. Oh, I can flip here, flip here, flip here, flip here. And I should mention one more thing when it comes to these operators. Why am I saying operators? Is that you can combine them to create a larger goal. So there are circuits out there that use solely logic gates to construct data. So I don't know if you know your processor architecture, but the ALU in your processor, the arithmetic and logic unit, if you want to add bits of data together, there's logic gates. There's ANDs, ORs, and XORs combined together in such a way to create a logic, to create an adder or a subtractor, or to create jumps, to compare things. It can all be done with logic. And it's all about knowing how to apply masks to bits to get the desired output. And that's it. So this has been Human Hard Drive. Thanks for watching.